In this video, we will cover a topic which in many ways is very relatable to everyday life. We will consider things such as heat transfer and entropy, which play a big role in cooking. More specifically, we will discuss the laws of thermodynamics. These laws are the culmination of hundreds of years of work by many scientists, and it was only in the 20th century that these laws took the form which we use today. Nevertheless, compared to some of the topics we will discuss later, thermodynamics is a rather old subject. A fundamental concept in thermodynamics is heat transfer. Imagine you have a block of metal at 20 degrees Celsius and another block at 100 degrees Celsius. If you put these blocks together, what happens? The same thing that happens when you put ice cubes in a glass of water. Hot always goes to cold. So in the case of the two metal blocks, the heat from the hot block will go to the cold one and heat it. The same thing happens in your glass of water with ice. The ice absorbs the heat of the water and eventually melts because the ice cube itself becomes too hot to remain in the shape of ice. This process of heat transfer stops when the two blocks of metal have the same temperature. This is called thermal equilibrium, which is when all objects in the system have the same temperature. Now we can extend the case of two metal blocks to three metal blocks and consider the Zeroth Law of thermodynamics. Let us label the blocks A, B, and C and put them together such that block A and B touch block C but not each other. Now the Zeroth Law states that if block A and B are both in thermal equilibrium with block C individually, thus if the system of block A and C have the same temperature and the system of block B and C have the same temperature, then A and B must also be in thermal equilibrium, even though they may or may not touch each other directly. This law is rather trivial from a mathematical perspective, as we can write A equal to C and B equal to C, thus A is equal to B. But nevertheless, this is an essential concept, and it's called the Zeroth Law. Next, one can consider the first law of thermodynamics. This law states that the change in internal energy of the system, delta Q, is equal to the difference between the heat supplied to the system, Q, and the work done by the system on its surroundings, W. So we write delta U is equal to Q minus W, where Q is the heat supplied to the system and W is the work done by the system. If our system is a pot of soup, then we put it on a hot stove. Then our system is not doing any work, but the stove is supplying heat Q to the system. Thus the kinetic energy of the soup increases and our soup gets hot. When the soup is hot, you want to remove it from the stove. If you lift your soup from the stove, then you, the surrounding, is doing work to the pot of soup, our system, thus the energy of the soup increases further. But this energy you gave the soup is now potential gravitational energy, thus the fact that you lifted the soup does not make it hotter, but the energy of the system is larger. Moving on, we can consider the second law of thermodynamics. This law has an enormous impact in our understanding of the world, and it's therefore very important. It is this law which gives processes their direction in time. We can write the law in an idealized way. Delta Q divided by T is equal to ds. This equation tells that the heat transferred delta Q divided by the temperature T is equal to the incremental change of the system's entropy ds. Thus, if we add heat to the system, S increases, and if we take heat away, the entropy decreases. For this to be true, the process must be reversible. The problem is that all macroscopic natural processes are irreversible. Thus, realistically, we should write the second law as dq over T is smaller than ds. This means that the entropy of the universe as a whole is overall increasing, always. It might be the first time you have heard the word entropy, and you might be asking yourself, what is entropy? In short, entropy is a measure of disorder. Many people have probably noticed that their room over time gets increasingly more messy and dirty. This is like an increase in entropy of your room. In order to fix this mess, you must do some work to return the room into its clean and organized state. Thus, you have to put in the work in order to restore this entropy. But the overall entropy is even worse, because for you to obtain the energy to do this work, you eat food, and the process of getting the food into your mouth has created even more disorder than the disorder you have removed from your room. The message here is not to say that you should not eat or to scare anybody. It is just to highlight that even though we can consider a process which for some limited system appears to reduce the entropy, the total entropy of the universe only goes one way, into more disorder. You might ask if there aren't any reversible processes such that the entropy does not increase. The interesting thing in physics is that fundamental processes are usually reversible, but things go wrong on the macroscopic scale because there are too many states for the system to be in, so it becomes statistically unlikely to return to the ordered state. Consider a simple example with some salt crystals and some peppercorns starting in an ordered state. If you mix this mixture around, salt and pepper will become mixed and the entropy increases. No matter how much you mix, you will not get your ordered state back. Why is this process irreversible? The problem is statistics. Every time you shake the mixture, you will get a new combination of where the salt and the pepper is located. The more salt and pepper you have, the more combination you have of how to arrange the salt and pepper. The issue is that there's almost only one combination, which is the original ordered state. Thus, the more alternative combinations you have, the less likely it is to ever return to the original ordered state. This is why macroscopic natural processes are irreversible. It is simply statistically unlikely to ever reach the original ordered state. Finally, we can discuss the third law of thermodynamics, which builds on the relation between temperature and the possible states or configurations. We can write S is equal to kBT ln omega. From this equation, we can see that the entropy S is the product of Boltzmann's constant Kb, temperature, and the logarithm of the number of microstates omega. From this, we notice two important things. Entropy is directly related to the amount of states. Thus, at absolute zero, there is only one state, the ordered state. Furthermore, entropy is a fundamental quantity, and temperature is not. Temperature is defined from the entropy, and this leads to the possibility of temperatures below absolute zero for quantum gases. But that's a video on its own. So, to recap, in this video we have considered the four laws of thermodynamics and how they impact our everyday life. We clearly see how many of these laws directly impact our everyday life. As we also discussed a little bit, statistics is the nature behind much of thermodynamics, and to go into the real depth of this field, it is also necessary to understand quantum mechanics. For now, it suffices to say that the physics of thermodynamics is incredibly useful in many aspects between cooking and studying the universe. If you like this video, please hit the like button, comment and subscribe for more. Stay tuned.